why do we study sun? Sun is our nearest star, and it provides us with a unique laboratory to understand physics. And particularly the younger audience, I want to give a flavor that it's just one astronomical object which we are talking about, sun. There are, of course, a number of objects. The entire universe is left with a lot of unanswered questions. So there is really room for advanced science experiments to be learned from studying astronomy in general. So an eclipse again provides us some opportunity to work or look at this atmosphere of the sun. What is corona? I will define a little bit in a few minutes. So we still, actually, Professor Hassan, who was our keynote speaker, he was my thesis supervisor many years back. So he has motivated to look at very intricate details about the physics in the atmosphere of the sun. And now I take this opportunity to go around the world, chase eclipses and do other stuff also. I will give you a flavor on that. And I will try to prove that science is exciting. So let's first look at what is this object in the sky called suns. Sun, its internal structure. There is something inside the sun as well. So first we need to understand what is happening really inside this particular spherical ball which you see, which emits all this light. Same with other stars. Why they are star and not planet and other objects? There is a difference what exactly happens right into the core. So this is where the thermonuclear reactions takes place. You hear about hydrogen bomb. Every second there are millions of hydrogen bomb is being exploded right inside the core of the sun, and that is the source of all the energy. So that is where energy is created, and then we have, this is a cut inside the sun, and you see this is the right in the core. Then the energy is propagated by radiation. You see, energy can be propagated in different ways. So radiation is again another way to propagate the energy. But these photons which are emitted here, they travel at the speed of light and they bounce so many times. It's like the random walk. It's a drunken man who walks and collides with another object, and it takes actually millions of years for the photon to come out eventually. And then the 30% of the inside, there is material, the energy is propagated by convection. The boiling of a soup and so on. I mean, you start with a bowl of water, you just heat up that, and then after a certain time, when enough heat is supplied, then you see the materials are churned back and forth. And that's one of the most efficient way of transporting energy from one place to another. And that is what exactly happens inside the sun. So that's the internal structure of the sun. And so here what I plot here is the temperature versus the radius. So this part is the interior, and this is my atmosphere. So what you see is where the thermonuclear reactions are taking place, the temperature is tens of millions of Kelvin. And then as you come to the surface of the sun, the temperature drops because the energy source is here and you are far away from that. So it's about 6,000 Kelvin. But again, when you go away from the surface, the visible surface of the sun, which you see actually on every day, if you look at the sky, what you see is the photosphere, that is the visible surface, that's about 6,000 degree Kelvin. But if you go to the atmosphere of the sun, like Earth has its atmosphere, sun has its atmosphere as well, then temperature again increases. And this is the mystery. What is the source of this energy? We know the source is right here in the center where thermonuclear reactions are taking place. So obviously a lot of energy source is there. But what is the source of this energy? How it is heated to that temperature? So this particular outer atmosphere of the sun is called the corona. And historically, this corona was only visible during the eclipses. There was no way you could see this emission. Also in the morning, Professor Hassan mentioned, and others also mentioned, that the emission from the corona is 10 to the power minus 6 times the emission coming from the photosphere. So if you have a very bright object, in the front, unless you block it, you cannot see the emission from the background. As simple as that. And the solar eclipses, total solar eclipses provide us with an ideal opportunity to block this disk perfectly, and it is also blocking very large distances away from the Earth. Professor Hassan also mentioned a point, scattering. What is scattering? You see, I mean, people will say, why can't you block it in front of your eyes? You see, you are just talking about blocking the solar disk. So why don't you block it just here and then see the corona? You can't, because if you block any object, you have a lot of scattered light, and that will not allow you to see the very weak emission which is coming from the corona. So of course, other opportunity is to go to space. You go to space, there is atmospheric effects are less, and in fact that is the experiment which we will be doing in few years. It was mentioned in the morning, and the co-PI of the mission for this. So we hope that we will be able to see the corona at our pleasure, anytime, all the time. So we will have a natural total solar eclipse, but still there is some limitations of those experiments, so we will still follow eclipses, chase eclipses. So what happens here, as I mentioned, as a physicist or solar or astronomer, because it's just not on the sun alone. There are millions of sun-like stars, and they have the similar behavior in their atmosphere, and we need to explain why they are hot in their atmosphere. And we have certain answers. I will give you certain flavors today. Going back to a little bit of history, you heard that eclipses provided us with a lot of opportunities to test fundamental physics properties. I mean, you have heard about general theory of relativity was verified during the eclipses. This is called of bending of light. Then you also heard that many a times that Fraunhofer, of course, first what you see is, in fact, we have this spectrograph. You can just build it very easily, using a DVD or a blank CD, and just use a black box, make a small little slit. The light falls through the slit and gets refracted, and you get a spectrum. And there, if you have you see, sun is a continuous source, right? And it has an atmosphere, and atmosphere absorbs certain particular wavelengths here. You see these dark lines, they correspond to each element in the atmosphere of the sun. So by looking at the absorption spectrum, this is called a absorption spectrum. You have a spectrum, you have heard about, I mean, you have seen, I think, VIBGYOR, right? You have seen, if you have done an experiment with a prism, with the light, you get the full VIBGYOR, right? You can also see in rainy days, in the sky. Suppose on this spectrum, on this light, it has to go through an atmosphere where certain elements are there, very highly ionized and so on and so forth. Then it will leave behind certain lines in the spectra. And that is what exactly happens in the solar spectrum. And believe it or not, there's still n number of lines in the solar spectra which are not identified. We still do not know as a physicist what is this line correspond to. What is this transition? Is it iron 13? I mean, you will hear about this, different transitions and all that. So the atomic physics community works on it, solar physics community works on it, and tries to find out new element transitions and so on and so forth. There's still a lot of room for younger people to discover more lines in the solar spectrum itself. So way back in 1930s, these lines were identified as highly ionized ions. So they identified from these dark lanes that these are very highly ionized lines, and when you get an ionized line, you can only get an ionized line when an element is heated up to very high temperature. You will not get these ionized lines under normal conditions. If you have temperatures of 6,000 or 7,000, you will have a singly ionized line. When you have a temperature of 1 million K, then you will have probably 12 times or 13 times ionized that particular element. So from that also, we can think about different temperature layers in the atmosphere. So 1850s to 1950s, it was also slowly evidence were building up that this atmosphere of the sun, which we call solar corona, is also magnetized. Magnetic field is there in many parts of the sun, and I will give you a much more detailed view soon, that controls the dynamics of the atmosphere of the sun. Not only in the sun, as I mentioned, the other similar stars will have the similar properties as well. And this gentleman, again, Dipankar, he proposed that hot corona provides enough gas pressure to counteract gravity and accelerate a solar wind. This is the word which he actually predicted before it was observed. You see, this is the beauty of doing often science or theoretical science, that a theorist sometimes come up with a idea and he says, you know, this should be seen at some point of time. And when that is experimentally gets verified, then only the theory gets fully established. You see, unless experimentally any theory is completely, you know, verified, that theory is not accepted. So it only, you know, initially will be called like as a conjecture or hypothesis and so on and so forth. So solar wind was something which Parker around 58 he predicted, and later on it was found out to be true. So solar wind is nothing but this sun, as I said, this atmosphere of the sun is also continually expanding. So it's also losing some amount of mass and so on and so forth. This is called a continuous expansion of the atmosphere of the sun. Now solar corona, you have just seen the pictures of total eclipses and so on, as I have given examples here as well. It's heavily structured as well. These are much closer. If I take a this image is taken in X-rays. There's another aspect of the coronal physics is most of the images what you see in the corona from the eclipses are called white light images, because the visible spectrum, whatever our you know, our eye are sensitive to, and which is coming to the earth, because the UV light and the X-ray light is cut off by our atmosphere of the earth, which is good for us, our existence, otherwise it would have been a problem. So basically the solar, you know, picture has really revolutionized after the space era. I mean, once we have been able to go to the space with rockets and satellites, we have been able to see the entire electromagnetic spectrum. Sun emits a lot of X-rays, sun emits a lot of ultraviolet rays and so on. So unless we were able to see those, we were not knowing that much about the corona. So more modern science is done with, you know, different wavelengths as well. This is very important. So these images, this is a particularly extreme ultraviolet image taken from a satellite called TRACE, which just died, actually been switched off a few months back, because there is an even better instrument on space now. And you see the corona is very structured, and what we understand now, these are looks like just, you know, tubes, right? And these tubes are magnetic tubes. These are not ordinary tubes. They are beautiful magnetic tubes with very high magnetic field strength of kilogauss. You know, the field strength at the base of these tubes are very strong. You can think about these are magnetic bottles. You hear about experiments in plasma physics community. They talk about tokamak and so on in the laboratories. You know, to construct a few meters of tokamak, it costs so much and so on and so forth. Here we have, you know, natural tokamaks of several hundreds of thousands of kilometers. So if you want to really study the physics, or actually these are all plasma state, this is the fourth state of matter. You understand, you know, everything when you heat up to a very high temperature, then, you know, it goes from gas to plasma state. So all this plasma is confined within this magnetic tube. And if you want to understand how this tube is evolving with time and so on and so forth, you have to follow what is happening in the solar corona. And that's what we do with modern day, you know, scientific experiments. What we do here, this is the plot of the temperature of the sun. As I mentioned, this is the visible surface called photosphere, and then temperature actually doesn't increase almost up to 2000 kilometers. More or less remains from 6000, it becomes tens of thousands. And this layer is called chromosphere. In fact, you have heard this name. This is also, chromo means color. And during the totality, historically what was happening was, after the second contact, what you see first few seconds is the chromosphere. This red links what you see, and also you heard about prominences and so on. That happens during the first few seconds of the second contact, and again last few seconds of before the third contact and so on. Before the corona is fully exposed, you see the chromosphere. That's how the name came as chromosphere. And then temperature suddenly, within a very small, you know, height, this is you know, height, and this is temperature. Temperature goes to very high temperature, millions of Kelvin, and this transition is, you know, sort of called transition region. And we understand now the physics of these layers are very different from physics of these layers, and that happens through a very smooth transition, which is not a very sharp transition as well. So I mean, to understand this physics, it's quite a detailed task. I will not probably go into too much of detail, but I will take you back. We heard a little bit of the very exciting talks in the morning about Copernicus and Kepler and so on. Of course, you heard about Galileo. Apart from discovering telescope, which I sometimes feel is a really big landmark for modern science, he also discovered sunspots. Through his own discovered telescope, he looked at the sun. There is a misconception or sometimes a controversy about how did Galileo lose his eyesight. Some people believe that he looked at the sun for too long, which is actually a controversial item. Some people do not believe in that. But what he did, meticulously looked at the sun and marked these black dots on the face. Each day, on consecutive days, he compared the images, and then he found that these dark black dots are not appearing in the same location on consecutive days. Why that is so? So then he said the sun must be rotating as well. So not only he discovered sunspots, these are called magnetic spots. These are highly concentrated magnetic fields. Now I will show you much details of the sunspots. And he also made it very clearly could calculate how much is the sun's rotation about its own axis and so on and so forth. What I wanted to show is that these sunspot, which appears as a small little dark spot now, we have a really very high resolution. It can be actually imaged to almost 1,000,000 times closer in a zoom up version. So I will skip that. In fact, this is also a movie. What it shows here, I will just depict this. Sunspots always appear as bipolar region. So this is nothing but like a tube. You have a tube, if you take a rubber tube and immerse it inside the water, what happens if the material inside the tube is lighter, it automatically comes up because of the buoyancy. I'm sure you have done this experiment and Archimedes' principle will push this material because it is lighter than the surrounding, it will come up. So similarly, these magnetic tubes which are sitting inside the sun, they, because of the property called magnetic buoyancy, this is very similar because these are magnetic tubes, because of the magnetic buoyancy, they come up and they appear as these kind of bipolar region. But here I am not able to play this movie. What happens is this is not a stationary object. Since it is moving up, if you give a little twist to this guy, then it will go, it will get twisted, and then if it is crossed with each other, then there is a different property called magnetic reconnection, and then you have a huge explosion. So all the time in the solar atmosphere, you have a possibility of such magnetic reconnection. Magnetic reconnection means, two magnetic field lines, they're coming and they're forced to come to each other. Normally, two magnetic field lines will repel each other. You have done experiments in the bar magnet, right? And you have the magnetic field lines which comes from the North Pole and ends at the South Pole and so on and so forth, right? So if you force two magnetic field lines to come together because of some flow or because of some twist, then the magnetic energy gets converted to a heat energy and you get a huge amount of energy release. So these are also called magnetic storms in the sun. Sometimes you will hear in the newspaper and so on and so forth that sun is very active, there was a huge storm in the sun, and when these storms happen in the sun, those energetic particles are thrown into the interplanetary space. And if we happen to be there on this line of sight of this storm, then it could be troublesome for us. So what can happen in that situation also, I will try to give you a flavor. So I will just skip because the movies are not playing. So normally what we do is, this is again a snapshot. You see, I was showing that this is a sunspot pair. As I said, sunspot always appears as a bipolar region. And now this is a telescope which is a optical telescope on a Japanese satellite called Hinode. What we do is, here we can measure the magnetic field what is there, which is responsible at the base, at the foot point of these magnetic tube, and then we can take images from different wavelengths. You see, this is the difference between most of the images what you were seeing in the eclipses are they're called all white light images. White light images means all the wavelengths are together. You cannot really make differentiation where exactly they are formed. But if you really want to do a detailed science or probe the different layers of the atmosphere, then what you have to do is you have to take images through different spectral window. You have heard about filters, right? What a filter, UV filter does, you know, well, a UV filter in your camera cuts off the UV light, but here we want certain, you know, wavelengths to only pass through that filter, and then we can image that particular thing. In fact, in the morning you heard, you know, again Professor Hassan was mentioning about red line and green line. These are two spectral line, which is highly ionized iron line, and if we take images from that to you know, filter, then we get precise information about the atmosphere. If you really want to do hardcore science, then sometimes you have to do those experiments. In fact, in the morning we heard about the linear polarization, not in the morning, afternoon, linear polarization. If you take a green filter, and then you can do good polarization science also out of that. The other question is that was about the sunspot. I was talking about the magnetic field, but sun as a whole also has a global magnetic field structure. This is actually a eclipse image. This is an eclipse image, and the state of affairs is now such that from before the eclipse day, even before the eclipse day, how the corona will look like can be predicted. In fact, this is done in, so John Linker and Zoran Mikic, in the Science Application you know, Corporation in the west coast of US, they have a simulation code which essentially has predicted how the magnetic field will be structured globally at that point of time. And we see very clearly there are certain places where field is open, and where there are certain places where magnetic field is closed. You see that wherever there is a magnetic field closed, you see this structure even from the white light corona, because more material is actually, you know, trapped there. The material is not readily, you know, able to escape from these places, and these are called the polar regions, where we find, I mean, in the sun also you have a polar region and an equatorial region. The polar region, you have the field lines more open. It's like an open channel, open tube, whereas this place, the field is more closed and so on and so forth. And as I mentioned, these are more newer discovery from, again, long-term satellite observations, that because of these structures, the solar wind, which I mentioned a few minutes back, also has a different, you know, structure. From the polar region, the wind which comes out with a much higher speed, whereas from the equatorial region, the wind comes with a much slower speed. It's like an expansion, and expansion is halted here because the fields are closed here, whereas this expansion is faster. It's easy channel to, you know, accelerate and escape from the sun because it is open field lines here. So these are some of the, you know, things which I just thought of giving you a flavor about. Then there is a big question is about this magnetic field, what we are talking about at the sunspot. Is it always the same? I mean, do we have the birth of the sunspot, or, you know, the sunspot is born and then it lasts for a few days and then it dies? Is this process always the same, or there is a difference in different times of in the past or now or tomorrow and so on and so forth? This is called the so-called solar cycle. It appears that this magnetic field of the sun is also changing with a periodicity of 11 years. Somebody in the morning asked about, you know, we always work for, you know, whether there is a periodic pattern of any variations. If there is a periodic pattern of any variation, then what is the responsibility? What is responsible for this periodic pattern? Here in the top panel, I'm sorry, the reproduction is not so good here. These are actually X-ray images here. What you see is that during the maximum means when sun is more active, that means sun has more number of sunspots, has more, you know, dynamic, more flares at these magnetic reconnections, and because of the flare there is material thrown into the interplanetary space. They are called coronal mass ejection. That means in the corona you eject some mass, so that's how the name has come, coronal mass ejection. So all these things happens more during the maximum period. So you have solar max, and then slowly as you approach the minimum period, then in the X-ray image it looks very dull. In fact, if a minimum time we take eclipse images also, it doesn't look so attractive because the corona is not very well extended. It is more, you know, constrained and so on and so forth. Whereas in the active phase, if you happen to have a total solar eclipse, you will see a lot of beautiful helmet streamers and structures and so on and so forth. So, and what is plotted here is the sunspot number. So you see, whenever there is a so this is a periodic, say this period is about 11 years, and there is one more aspect, that when there is maximum period, the CME is what we talked about, can happen from anywhere from the sun, whereas in the minimum phase the CMEs and because the sunspots appear only in the lower latitude close to the equator, they do not appear to the higher latitude. CMEs do not come from the higher latitude. Here actually what is shown here, these objects are called coronagraph. You heard in the morning as well. So coronagraph is nothing but occulting the solar disk. It's an artificial eclipse. It's very much similar to total solar eclipse, mimicking a eclipse kind of situation. But in the case of a device which we put it's normally in the satellite, these are called internally occulted because the occultation happens within a box and so on and so forth, whereas in the natural total solar eclipse it is the external occulter because the occulter is much away from the receiving end where our detectors are. So what happens is, suppose I see this is the magnetic images from I can't read the 1992 to 1999. 96 was the minimum period. You see these are magnetic map of the sun. So a magnetic field was high and then it went to very low values and then again became higher up. So if I just overplot on that the X-ray images, it's exactly the same. It's very active during the X-ray, I mean into the maximum period, minimum period you hardly see any X-ray emission and again it repeats. So you can see the majority of the activity what happens in the solar or the excess emission what you see in the solar atmosphere and so on is all due to the presence of the magnetic field. So if suddenly magnetic field disappears, then we are in trouble. So this is again has a long-term implication about this. If I go back, this is 400 years of sunspot observations from 2002 way back in 1600. Historically, what was found that Maunder was the discoverer of this particular effect, and he reported that during 1650 to 1700 there were hardly any sunspots. You see, sunspots have been recorded by Chinese and other people for centuries actually. Few hundred AD onwards they have been observing actually sunspot. So this was a period over which the Volga was frozen for 40 years. Volga is one of the major rivers in the Europe, and it was very cold in the earth. There were several thousands of people died. So obviously there is a direct impact if suddenly something changes in the sun. We talk about global warming and so on and so forth. I mean, there will be catastrophic effect in the earth. Fortunately, sun doesn't change even 0.1%. If the solar radiation, which is called the total luminosity of this star, is changed more than 0.1%, that could be disastrous for us because we are really existing because of the presence of the sun. So how about last solar cycle? I'm just plotting here. This is the sunspot numbers, and then it was predicted that the sun will be active from again around 2008 onwards. But in reality what happened, so this was the minimum period, and in reality what happened, sun was inactive for 2 years. There were hardly any sunspot. Just very recently it happened, just 2 years back. And we were really worrying, are we getting into a Maunder minimum kind of situation where if the sunspot doesn't appear, then probably global warming is not going to be a problem for us because we will be cooling down because of the sun's less magnetic field. So again, from the minimum to maximum, you see this is the overall solar image in EUV, extreme ultraviolet image. If you take, you see always anytime you can take the image from the space, and you see minimum period this is like this and maximum period this. This is the coronagraph images. Here also what you see is this is a smaller occulter. If we were listening actually in the morning that you can have images from smaller field of view and larger field of view and so on. Here it is exactly the same. This is a more inner corona and this is a very extended corona. You can see up to 10 solar radii here. During the 1996, what I was mentioning here, that you see all the CMEs actually only constrained in the equatorial region, whereas in the maximum, if these radiations, what you saw, these are coronal mass ejections. So if this material comes towards Earth, fortunately for us, Earth has its own magnetic field also. This is the if there would have been a bar magnet in the center of the Earth, this would have been the lines of force. But basically, what the Earth's magnetosphere looks something like this, because from this side the solar wind is coming, and associated with the solar wind, there is also these coronal mass ejections and so on and so forth. So all these actually perturb this, in this particular magnetic field lines, and we have the solar influence felt here. So we are actually shielded here because of the presence of the magnetic field. So last few minutes I will just give you a flavor that with all this background from India, we got this opportunity from a ISRO call that we could do some experiment, a dedicated experiment from ISRO platform, and we quickly designed that. You have seen this particular slide, I mean snapshot in the morning also. So we designed to build a coronagraph. This is a coronagraph in red and green line. So it's again with a very specific temperature response of the corona. All the time we will have it with a very high cadence. We will take images of the corona few frames per second. So the current coronagraph in space takes images at 12 minutes per frame. That too, it is a white light, because ours is a dedicated satellite. We have telemetry and so on and so forth. We have better modern CCDs and so on. So we will be able to take images every 300 milliseconds and so on. So this is a really different ball game altogether. These are called sun synchronous orbit and so on and so forth. So again, for the younger audience, these are enormous opportunities for India. I mean, I'm actually really fortunate to be back in India in right time and getting involved with this kind of mega project, and the future is very bright as far as in India is concerned. I mean, there are some foreign guests here. I think this is a golden period for science in India now. I mean, the opportunities, I mean, this is unheard of. When we say about proposals, they say money is not a problem. So this is really wonderful, because I lived in Europe for several years. Always we used to spend half of the time for proposals. Here if you have a good proposal, it's really very, very supportive now. So the system is very supportive for doing good work. So opportunities are there. You have seen this lake. This is actually in Himalayas. Probably most of the students have seen Three Idiots. So this is the last shot of Three Idiots, which was shot in front of this lake, Pangong. So we are not allowed to do such exercises, but we have several, and I have spent a couple of winters here actually. I was not allowed to stay more than 15 days, but it's a fantastic place to even visit for a few days. And I have been now part of different eclipse chasing. In fact, I was fortunate to be the first student to be chosen for 1995 eclipse. I was with the Russian aircraft An-32. So this was the first experiment for the Ministry of Defense to chase eclipse. It was really not a chase, because I'm probably the first civilian to be allowed with a transport aircraft. There was a MiG as well, but we were not allowed in the MiG. So we gave our camera, but I don't know why they could not manage to take pictures. I tried actually polarization experiment, but it was too hard because the aircraft was not too stable. But incidentally, what happened, I was sitting in the pilot seat, and the Doordarshan crew was there. Doordarshan is our national TV channel, and they were picturing the entire thing. And then afternoon it was shown on the TV, and my mother saw it, and with the big audience, she said, "Oh, that's my son." Then everybody was saying, "Come on, you are seeing your son everywhere. I mean, this is a pilot, it's a military aircraft." But that's really my fortune, that I was sitting on the autopilot mode. I just opened the the window on the side, and was allowed to go out and take pictures. But that's experience, I would say. So since then, 95, then China, recently Easter Island, we have wonderful experiences. And I'm actually also must say that there are certain experiments which can be done during eclipses. They're a bit tricky in terms of they're still bulky, because you have to have a spectrograph. I mean, if you want to do some characteristic properties of the corona, images alone doesn't provide you the full science. So you need a spectrograph, and that is a little bulky in the current context. But we should have much more modernization to get it along. So we have a very big opportunity of building the largest solar telescope if it is approved, and then of course eclipses. Australia also probably will be there. We are there.